So today we begin the study of the postulates of quantum mechanics, and this will be spread over 2 lectures. And so let's begin. So let's start with questions from classical physics. There are 3 questions which one typically asks. How can one specify the state of a system at any given time? Then, if we can do that, what can we say about the state at a later time? And then we usually, any system, we make measurements, and so the question is, how do we go about making physical measurements, and what are the quantities that you can measure? So let's take an example rather than be very, very abstract. So we'll just consider a particle of mass m moving under the influence of a conservative vector field, and we know the answer for this. You need to give the position and momentum of the particle at a given time. And in case you know what phase space is, this is just a point in phase space, which is just a space of all positions and all momenta. So you've got to give me a point, and Newton's laws tells you how to evolve the system in time. So we will write this as 2 equations rather than 1. So it says dx by dt is p over m. This is kind of an obvious relation, but we should write that. It's a differential equation. And the other equation is dp by dt is minus gradient of the of a potential. And so in principle we can integrate this, and it's a first order differential equation in 6 variables if it's in space. And physical quantities are typically functions of x and p. So in some sense, the pinnacle of this ideas goes back to a book written by Lagrange called Mécanique Analytique. It was written. It is a 2-volume which appeared in this period, 1788 to 1789, and it sort of was pushed Newton's equations to a much more general setting. And the point which I want you to remember is that it gave an analytical method by which every mechanical question, and maybe even non-mechanical questions, may be stated as a single differential equation. By the way, by single differential equation, it could be this can be thought of as a combined single differential equation. What you can do is you combine x and p and write it as a column vector, and then you can write it'll be like d by dt of some column vector equal to something. So it becomes one big differential equation. So that's the idea. And this differential equation, and as I mentioned, it's a system of equations. They generalize Newton's law to a more general setting and are called the Euler-Lagrange equations of motion. The amazing thing is that Maxwell's equations, which is not mechanical, also fit the general framework of Euler, Lagrange, and many others. So but 2 developments came along which completely sort of made this view look archaic. And just to make an analogy, if you remember, Archimedes claimed that if you gave him a long enough lever and a place to stand on, he could move the earth. Similarly, this statement here says that if we can solve this differential equation called the Euler-Lagrange equations, or EL for short, we could answer everything about it. But it turns out this is not entirely true because of 2 reasons. The first one is a classical thing. It says chaos or exponential sensitivity to initial condition. So recall that if you're given an initial condition, that is a point in phase space, solving the Euler-Lagrange equations gives you a trajectory of the system in time. However, we know that there will be uncertainties in measurements, and one can only specify the initial condition to some degree of accuracy. Now comes the kicker, which is that there exist systems where 2 points very, very closer than, say, your experimental accuracy to each other at some time, initial time, will have trajectories that separate exponentially fast. That means they diverge. So if you make a small mistake in your calculations, you will be off by a huge margin. So this says that you really cannot predict things. But at some level you might think that this has to do with the fact that if we could measure things more accurately, we could do better. Okay. Then comes quantum mechanics. Quantum mechanics makes things even worse. It puts fundamental, and not just experimental, but fundamental bounds on what can be measured. For instance, in this classical setting, we saw that if you give me initial condition was to specify a point in phase space, In quantum mechanics, we can't even do that. And so we will be studying some of the ideas behind this in the next couple of lectures. So there are three quantum questions for quantum physics. It's exactly the same questions that we asked for classical physics. How do you specify the state? What is its evolution? And how do you measure quantities? And we'll answer these questions in the form of three postulates, and each one will address one of these questions in this order. So the first postulate is about the state of a quantum system. Postulate 1, which is about the state of the quantum system. The state of a quantum system is a vector, which is sometimes called the state vector, in a complex inner product space, Hilbert space more generally, which we will denote by H. This is the first postulate. It's completely different from what we saw in classical physics, where it was just a point in some space, the phase space. When the dimension of inner product spaces become infinite, issues such as convergence become important. So Hilbert spaces are inner product spaces, but there are additional conditions that become relevant for infinite dimensional spaces. Finite dimensional case Hilbert spaces can be used interchangeably with inner product space. And complex nature is also important, as we have actually seen in some contexts. So now the question is, how does one figure out the relevant Hilbert space for a system? We will illustrate some of these ideas through examples. But there's one more thing. It's not the state is not just arbitrary vector, but suppose you have two state vectors, v and w, ket v and ket w, which differ by a scale, where lambda is some non-zero guy. Lambda cannot be 0. That means if lambda is 0, v would be 0. So that's not. So lambda should be something non-zero. Then these two are the same state. So what one does usually is to normalize the vector v. So use this freedom. Suppose you're given w, you replace it by v, and you choose lambda such that this has unit norm. But still that only makes use of the real part, and there remains the overall phase. And what you do is that you argue that this phase is not physically relevant. Okay, so let's begin with an example which I'll now call qubit, but it's just our Stern-Gerlach experiment. So we begin with the spin-half system. So let SS, we'll use this short form for classical state space actually, SS. And this is the two outcomes of the SGZ experiment or coin flip. So we might label the set in many different ways. So up and down for, or plus H bar by plus or minus, heads or tails if it's a coin toss, or 0 or 1. So, but it's just a matter of taste as to what you call them. Key point is that this set has two elements. And now, for instance, just to change things, we'll use the 0-1 representation, call it the bit space. And this is just from coding theory, where you have bits, and bits can take values 0 and 1. So the Hilbert space is C of SS, which is nothing but to every element of the set 0, we associate one basis vector 0, and similarly a ket 1, which represents, and this will be an orthonormal basis, and the span of that will be a complex vector space of dimension 2. And of course, once you pick a basis like we have, it is just nothing but C2. And this space, we'll call it the quantum bit or the qubit space. Okay. How about an arbitrary state vector then? It has to be psi, which is some a times some linear combination of 0 and 1, a times ket 1 plus b times a times ket 0 and b times ket 1, and a, b are just arbitrary complex numbers. So, but remember we said that we can use this normalization, we can make this to have unit norm. So I'll just trying to use ideas that we had from usual vectors, where we put hats for unit vectors. We will put a hat here to remind us that this is a normalized vector. So psi hat, if you do this, you just divide by square root of mod a square plus mod b square. But of course, there's an arbitrary e power phi, which is the arbitrary phase, and you can't fix that. You put this, you can see in the norm, there'll be e power minus I phi coming from the other guy, and this will cancel from the bra, and so this will go away, and the norm will be 1. It's very easy to check. So this phi should not be observable. Similarly, we can generalize to multiple qubits or a system of n spin half particles or n bits. Okay, the classical state space is now of the order of 2 power n, because each spin or bit can take two values and there are n of them, so 2 power n configurations. So SS, I'll just put subscript n to remind you that it's an n-bit space, now can be represented. This is the advantage of writing it in binary form in terms of n-bit number, so which is B1, B2 up to Bn. So B1, B2, each of these can take values 0, 1, and I goes from 1 to n. So now what you do, the Hilbert space is again, to each of these numbers, you associate a ket vector, and this is supposed to be an orthonormal basis. So we have an orthonormal basis, and its span will be some Hilbert. We'll call this a Hilbert space. And what is the dimension of this Hilbert space? It is 2 power n. So for 2 qubits, H2 will be span of 0, 0, 0, 1, 1, 0, 1, 1. So again, you can write the normalized vector. Oh, there's a typo here. I'll fix it in the slides later. And so again, there's this overall norm. But now A, B, C, and D are complex. So we have to divide by the norm. And it's just simple exercise to check this. Third example is that of a spin J Hilbert space. This is not n spin half particles, but it's a single particle. Some atoms may have higher spin, so the SZ component of the spin angular momentum of a spin J, and spin J can take half integral values. That means it can be 0, half, 1, 3 half, 2, so on and so forth. So that generalizes spin half case which we saw. And now it can take 2J plus 1 values, and it's quantized in units of h bar, so it will be m times h bar. So the values it can take, m values, are minus j plus 1 up to j. So you go in steps of 1 and you can see that these are 2j plus 1 values. In particular, if j is half, you would get minus half and plus half. That agrees with this. For instance, if j was 1, we'll get minus 1, 0, plus 1. It will be 3 times. So a Stern-Gerlach experiment for this kind of thing would have 2j plus 1 possible outcomes. Now again the same thing, the Hilbert space is just the same trick that we had. To each of these possible outcomes, you introduce a basis vector for orthonormal basis. So you get 2j plus 1, so you get a 2j plus 1 dimensional Hilbert space. For instance, the z component of orbital angular momentum also is similar, but now the analog of j, half integral things are not allowed, so half is not allowed, but 1 is allowed, 0 is allowed, 1, 2, 3, so forth. And these are the possible values that are allowed, so you can go, I stopped at 3 here, but you can go on 4, 5, all integer values. And in quantum chemistry, you would have these are called the S, P, D, F, and so on and so forth. Thus, if L equal to 1, ML would be minus 1, 0, and 1. So I'm just putting a subscript L to remind you that it has to do with orbital angular momentum. Later, maybe if I want to distinguish with spin, I'll put MS for spin. The next one is Young's double slit experiment with electrons. And this example is meant to be pedagogical, and we'll only discuss a caricature or cartoon of the full double slit experiment. Full double slit experiment is in all of space, but we will just focus on the screen, and even the screen we will take it to be just the x-axis, just one line on the screen. And so now the classical space of states of electrons, so we are interested in where the electrons will go and hit, and every place it hits you get you'll see a bright spot on the screen, right? So SS in this case, the state space is all values of x which lie in the limit go between minus infinity to plus infinity, which is nothing but the real line. The order of this set is infinite, and now we have to start thinking about what we have to do. So the vector space C of R we can again do in some crude fashion. Just say blindly for every point here we associate a ket vector, and so we have and see R is something like the span of this thing. But it turns out this is too large, and orthonormality itself becomes a problem to define, because this x has a continuum thing, it's not discrete. And that can be fixed by saying that we take some points with some spacing, and integer points with some spacing a, and just take a to 0 at the end. But let's forget that for a moment. That we can handle. But the key point is that it's too large. This space is too big. So let's just kind of naively push things. So we'd have, let's assume that x was some discrete thing. So the first line would be psi, you would expand, and for every x. So now instead of writing psi subscript x, I'll write it as psi of x. And so sum over all possible values of x, and this would be just the coefficient. This would be a generic state. But now we know x is continuum, so the naive guess or whatever is just replace sum by integrations. Okay, and let's just sort of be crude and let's assume this is possible. Okay, so psi is some integral, of course, from minus infinity to plus infinity dx psi of x. So, and let's just call psi of x the wave function of the state psi. Okay, define the Hilbert space to be the subspace of function psi of x such that there is a finite norm. So you can think of what I'm giving as a definition of norm or inner. From this we can even get inner product. So norm square of this state psi is nothing but minus infinity to plus infinity dx of mod psi of x whole square. This has to be finite. Okay. This space, so this is clearly a subspace of C of R. It's this space is denoted by L2 of R. There's a more generalization called LP, which so from that point, but just this is standard notation, and the state and R is just the state space. We put it in here, and it's called the space of square integrable wave functions because it's a mod square. So this 2 has to do with this. So more generally, P means you put mod psi power P. Okay, but for us, L2 is only relevant. So in analogy with the Young double slit with light, the absolute square of the normalized wave function. So now I put a hat here to remind you that first thing is that since this is finite, I can divide by this thing and kind of create a unit vector. If it were infinite norm, we cannot even do, create a normalized guy. So now this has an interpretation. Mod psi hat x square dx is the probability of the electron being found at x between x and x plus dx. Or equivalently, if you are comfortable with probability density, mod psi hat square is the probability density. Now let us think of the go back to the double slits experiment, even in this case also. So there are 2 slits, and let's say we close one slit and then we get some pattern, and that pattern, just following this, let's call that pattern something like psi 1 of hat of x. And so mod psi 1 hat square will give you the probability of finding the electron on the screen coming from slit 1. Similar experiment, close slit 2, 1 and look at slit 2, you get psi hat. And superposition principle says that psi of x, the answer for the double slit experiment, is the sum of the normalized guys. Okay, here it's important. This psi of x as it stands is not normalized. We can normalize it. And this is important. And now the point is that we have a Hilbert space which at some level is an LBS, so superposition makes sense. So you can see that superposition is built into our basic construction. Now let's do something completely different. So we'll take a one-dimensional particle. Again, this is for simplicity. So classically, the state space is the phase space. Here, what is it? It's x, and the momentum, I'll just put a subscript p of x, subscript x for this. So x p of x, this is a set of points in R2 because x goes from minus infinity to plus infinity, px goes from this thing. So what should be the state space? This is what we would think, the space of all position and momentum. So this would be our guess, C of R2, but this turns out to be incorrect. And again, you have heard about this, but I'll just state it. In the quantum mechanical world, the Heisenberg uncertainty principle operates. So the correct space, so really it says that you cannot put a point in x and p. You cannot do that, but the best you can do, you could choose either x or px, but not both. So the correct space is either the position space or the momentum space, but not both. And to match with standard things, we will work with position space, but the same description will go through in momentum space. Okay, but for this talk, for simplicity, we will stick to choosing position space. So the Hilbert space for the quantum mechanical one-dimensional particle is L2 of R. Again, they should be real valued, so I messed up here. But this, you can see, is the same as what we saw in this context. It was also L2 of R. Okay, so So now, so we'll just use the Hilbert space is the same as that of the double slit experiment. And again, the normalized wave function is interpreted as a probability density of finding the particle at location x. Similarly, if there's a particle moving in space, the Hilbert space is L2. Now the state spaces are, the relevant state space is R3, not R6. And what is this? This is the space of square integrable wave functions on R3. And so you just do now replace integrations of 1D integrations to 3D integrations. But this is the same kind of norm, and this has to be finite. So that concludes our description of the state of the system, and we have seen 5 distinct examples, and a few of them are infinite dimensional. Now, the next step is to tell you, we know how to specify the state of the system, but now we are interested in asking what happens next, what will be the new state of the system, and this is what we'll call time evolution of a quantum state. So this is postulate 2, it's time evolution in quantum mechanics. And I'll state it in 2 different ways. So we'll just choose the first one way. Given a system, a quantum system, of course, in the state psi of t0, which belongs to the Hilbert space at time t0, the state at time t greater than t0 is given by a unitary operator u. It has 2 arguments, u of t and t0. So it is in the following forms: ket psi of t is equal to u of t t0 acting, this is a linear operator, of course, acting on this ket vector, ket psi of t0. Obviously, if we take t to t0, it should be identity. And for t greater than t1, which is greater than t0, so this t1 is some intermediate time, we can first, so you think of this as u here evolves it from t0 to t1. So we can do the evolution from t to t0 in 2 ways now. One, go directly from t0 to t. The other one is to go from t0 to t1 and then t1 to t0. And this evolution should be compatible. I mean, this is obvious. And we know many things. We know that if you have 2 unitary operators, their product is unitary. So each one of these are, of course, unitary. And this kind of thing has to hold. Okay. So this is kind of nice. So we have this operator is unitary. Another thing, property of unitary evolution is that the norms will not mess up. So if you start with finite norm, you'll remain finite norm. If psi of t0 is normalized to unity, this will also continue to remain normalized to unity. So let us now ask what will happen if we ask for some infinitesimal time. Epsilon will, for simplicity, we'll assume epsilon to be greater than 0. We can write u, so what I'm saying here is you have t and t plus epsilon, so the argument. So I have some time t and some very arbitrarily close time, asking what this thing can be. So now we just do Taylor series in epsilon. So you'll have 1, that is 0th element, plus I by h. So these are just constants. So I h bar, so this is just conventions, times some operator h of t times epsilon plus Taylor series would go on, but we are truncating at order epsilon square, we are throwing out. So we are just focusing on the first correction to this with respect to unity. Now you can actually prove it's h of t, not t naught, where h of t is a Hermitian operator if u of t plus epsilon t is unity. Converse is also, I mean, so this is kind of nice. It says that h has to be Hermitian if u is unitary. Okay, so this is a very beautiful connection. We will develop on this later, but that the unitary operators and Hermitian operators have this kind of nice relation. So then if you go ahead and plug it into this, you can convert this and do the standard. You can ask how does, using the properties of derivative, you can ask how does this evolution translate to small epsilon, by which you can write a differential equation. This differential equation is something you would have heard about. It's a Schrodinger equation, and it's written as I h bar d by dt of ket psi of t is equal to h of t. This is the same h of t, psi of t. So this equation is the evolution equation. So this is like a differential equation. So this is the analog of saying of Newton's equations, which we saw, that d by dt of the 6-dimensional vector x and p was equal to some other thing. Okay, so that's similar to that. So we have a first order differential equations, many changes, of course. There is I is very, very important. I out here, It shows that we are working in complex vector spaces as well. H of t is called the Hamiltonian operator for the system, and we have given it a time argument because it may have explicit time dependence, but the large class of examples we will look at, H will be independent of time. So exercise for you: show that the Hamiltonian H of t has the same physical dimension as energy. Okay. Now when H of t is independent of time, you can easily show that U of t naught takes a very, very simple form. It's exponential of minus IH times t minus t naught into h bar. Okay, so you can check this U satisfies these two properties very easily. And here we have actually introduced this operator, which is exponential of another operator. It makes sense that you can just think of it as a formal definition. So if A is a linear operator, any linear operator, not necessarily Hermitian, unitary, anything, we can define this. E power A, and so you choose a basis, it becomes a matrix. So E power of a matrix is formally written as summation of m equal to 0 to infinity A power m factorial. What is A power m? You act A m times for any linear operator. And actually it turns out that this has infinite radius of convergence, similar to E power x being defined as summation x power m upon m factorial. Okay, so this is just a generalization. So it's just, this is a beautiful way of writing it. Now, when psi of t naught, again this should be psi of t, is an eigenvector of h, so let psi of t naught be an eigenvector of h with real eigenvalue e. H being Hermitian implies its eigenvalues are real, so actually it's tautology, but I'm just emphasizing that. Then you can go ahead and h acting on psi of t, you will end up with the time independent. So, well, this is not the time independent Schrodinger equation, but I can, this is wrong. It's just the Schrodinger equation h psi, this equation just says that h of psi, and it becomes E of psi. And so then you get a simple solution which says that psi of t is equal to e power minus, so h, wherever we see h, you can put e, it's just the same thing acting on this. So it's just a phase. Okay, and we saw that the overall phase of any state is not physical. So we can say that the state remains in the same state. So such states are called stationary states. So if you give me h, if you give me a Hamiltonian, I can work out its eigenbasis, basis of eigenvectors. That will give an orthonormal basis. And if you put your system in any of those eigenvectors or eigenstates, then its evolution will be very, very simple. There will be a phase, time-dependent phase, and that's about it. So in isolation, this is boring, but now let us look at more complicated things. So we'll do this with an example. So let's go back to our spin system, and the Hamiltonian is something which you would have seen as energy. So this is like minus m dot b. So h, now it's an operator here. H is a Hermitian operator, and h is minus g mu b s vector dot b, and we are going to take b to be along the z direction, so with magnitude b. So we'll just write this as minus g mu b is Borg magneton times b times sz, and we'll just define this quantity in red to be omega. You can check that it has dimensions of angular frequency. Okay, so with the minus sign is important, so that is there. So this is what we get. So this is our Hamiltonian. It's proportional to sz, and the proportionality constant is minus omega. The stationary states are, of course, the eigenstates of sz. So these are just sz plus and minus. And what are the eigenvalues? So when it is plus, sz is plus h bar by 2. So the eigenvalue is E equal to minus h cross omega by 2. And if it is sz minus, E is plus h cross omega by 2. So the lower energy state is plus, the higher energy state is minus. Okay. So now, what can we say? If psi of 0 is at time 0 is sz plus, then it says that psi of t will be e power plus I omega t upon 2 sz plus. If it is minus, then you will pick the minus sign. So again, the sign evolution is simple. But now here's where the fact that we are in a linear vector space, and sz plus and minus give you an orthonormal basis. Means if you give me any arbitrary vector, I can expand it in the basis given by sz plus and sz minus, and two arbitrary constants a and b can be put in there. And it's not particularly important whether psi is normalized or not, because as we know that the evolution is unitary, norm will not change. So you can think of a and b such that this is normalized, but that is not so important. But what is important here is a and b are some complex numbers. That's it. So from psi of t, what will happen? So let's look at this. So psi of t will be a times the unitary evolution of psi z plus, which is e power plus I omega t by 2 times sz plus. Similarly, this guy will evolve with a minus I omega t by 2, and this b just goes for the right. So that's what happens. So at time t now, so if we know the evolution of the eigenbasis of the Hamiltonian, and eigenbasis, I'm using short form, this is like the basis of eigenvectors of the Hamiltonian, eigenbasis or whatever. Okay, so psi of t, now I can pull out this overall phase, and then you get a sz, get sz plus e power minus I omega t times b times sz minus. So the overall phase is not important, but the relative phase shown in red is relevant. So now this is where you need to keep track of this. I mean, it's not like I can throw it away. If I were only considering states which are eigenvectors of H, then yes, we need not worry too much about this phase. But if you take things arbitrary states, they are not eigenvectors of H. So we need to keep track of the phases, and again, there will always be some overall phase which you can forget about, but you can look at the relative phase. This is important. And so we can, let's see how does this work. So we can, I'm just going to choose omega t to be 0, pi by 2, pi, and 3 pi by 2, and ask what do these states look like, and I'll choose a, b to be 1 by root 2. So now it's normalized, etc. So at 0, what is it? It's szx plus sz minus upon root 2, and this we saw was sx plus. I leave it as an exercise for you to check that at pi by 2, this becomes sy minus, and then at pi it becomes sx minus, and 3 pi by 2 it becomes sy plus, and at 2 pi it comes back. So actually you can show that this particular state is eigen state of n dot s, where n is this vector which is rotating clockwise at t equal to 0. It's a unit vector which is pointing along the x direction. Then after if you wait till pi by 2, it rotates and hits the minus negative, points along then the negative y-axis, then points along the positive x-axis, the negative x-axis, and comes to the positive y-axis and back. So you can actually show something much more general, but this is kind of easy. Kindly check this. So now we are ready to handle general time evolution, and let H be a Hamiltonian for a quantum system with an n-dimensional Hilbert space, calligraphic H. So since H is Hermitian, its eigenvalues are real. So let us choose phi I to be some orthonormal basis of eigenvectors of H with eigenvalue Ei equal to H cross omega I. And of course, you know, if two eigenvalues are real, you need to do some Gram-Schmidt. We'll assume we have done all those things. We have done some kind of Gram-Schmidt. And so we have orthonormal basis. So phi I equal to 1, 2, 3 up to n will be eigenvectors with eigenvalue H cross omega I. So this is just dimensional ground. So this will E as energy, dimensions of energy. Then omega I will have dimensions of angular frequency. That's why we are calling it omega. These are the stationary states for quantum evolution. Now we can say, suppose at time 0, arbitrary state can be expanded. Now there will be n coefficients. And AI is trivial or a thing that you can take the inner product of the state with phi i's, and lo and behold, because it's orthonormal basis, it will pick out AI. So there's some very useful property of orthonormal basis. That's why we always work with it. Further, now we can easily write. So what does it say? We can do the time evolution. It just says that the ith guy will go like e power minus I omega t. So E by h bar into t, this is what this formula said. Right? So, but E is some h cross omega I, so h crosses cancel, but there's a minus I, so that's what we are doing here. So, but each of these basis vectors evolves with a different angular frequency omega I, so you get some coherent superposition, and this is your answer. So now we are able to answer. You give me a general state at some time t is 0, and here, lo and behold, we have the answer. Provided we are told what are Hilbert space is, that means we know which state it is. The state space is known, quantum state space, and we know the time evolution operator or the Hamiltonian. So now we will look at two examples from chemistry. First is the simple harmonic oscillator. When I say examples from chemistry, I believe you learned this in chemistry. So H now is L2 of R, and the Hamiltonian is given by the Hermitian operator H, which is minus H cross square by 2m d square by dx square. We've already seen how derivative and higher derivatives are linear operators. Similarly, this is plus half m omega square x square. X square is just, x is just the operator, which is multiplication by x. Again, you can check this a linear operator. We didn't look at this in terms of in polynomials because we could have, because if you multiply with x, the degree goes up and you might go out of the space. So if you start with polynomials of degree n and you take x power n and you multiply it by x, you get x power n plus 1. That is not in the space. So it was x can't be defined in such a thing. But now we are looking at all functions. There's no condition that way, and we are looking at square integrable functions, and so multiplying by x might make sense. So this is a Hermitian operator, and the eigenvalues of this operator, we are not going to prove this. I mean, this is way out of our this, but we can state the results. En is equal to the energy eigenvalues is n plus half h cross omega. So n goes from 0, 1, 2 up to this thing. So the ground state energy is n equal to 0, which is half h cross omega. Each eigenvalue appears only once. That means the degeneracy we say is 1. And let n, now I'm changing notation, I should call this phi n, but because this I think is ket n, denote the corresponding eigenvector. So ket n has energy eigenvalue. H acting on ket n is En times ket n. Thus any state now can be expanded in this basis. So psi, you give me any state. So we have already seen that if it is L2 of R, we could write it like this. So this would be that wave function fellow. And now we can go ahead, but this is our statement, but now it's infinite dimensional. So n equal to 0 to infinity an of ket n. So this is the basis we would like if you're going to do time evolution. This is not a nice basis in that sense for time evolution, but this is. But now we can just ask how are these related, and so you can just say that n can be written as phi n of x. So phi n here we will call as the eigenfunction of h, and it's just one-to-one correspondence. It's the same as ket n, it has the same information. And psi of x, the wave function for this is just summation a n phi n of x. This is just some algebra which you can do. And we can look at detail of this function. Again, you may have seen this. Hn of x is hn phi n of x is proportional because it's usually normalized, but this is not normalized. Hn of x upon x naught. So x naught is this length scale in the problem. This is a beautiful exercise. Given n and omega, you cannot create a length scale, but once you go to quantum mechanics, you get a new parameter which you can add called h bar, and so from that you can get a length scale in the problem and everything. So x by x naught is some dimensional variable, you can call it y, and it goes like e power minus y square by 2. This is called a Hermite polynomial. Okay, again this is just a name, you may have heard about it. So what I'm saying here is we can solve for this, get this thing, and we can have explicit formulae for the eigenfunctions. This is the first example. The second and last example is the hydrogen atom. Now the space is L2 of R3. Hamiltonian is minus h square by 2 me, which is the mass of the electron, del square minus e square upon r. We are working in CGS units or Gaussian units, so k is 1, so it's just e minus e square upon r. And the eigenvalues are this minus this whole funny combination is Rydberg upon n square, and n, which is called the principal quantum number, takes values 1, 2, 3. Okay, so now we can ask, what can we say about the subspace of A of H with energy En? So it turns out that this is not one-dimensional, but it has dimension 2n square. So if you take n equals to 1, the space is 2-dimensional. If you take n equal to 2, it will be 8-dimensional. If you take it to be 3, it will be 18-dimensional, so on and so forth. These numbers you would have seen. Now, states in this subspace are distinguished by eigenvalues of other operators such as orbital and spin angular momentum. Eigenvalues are also called quantum numbers. Eigenvalues of, so n we already know, so there are additional quantum numbers. L is like the angular momentum square, it's related. ML is the LZ component, and MS is the spin of the electron. So these are the, so now you see there is ML and MS, and what are the possible values? Fix n and ask what are the possible values L can take and ML can take. So if L can take values 0, 1 up to n minus 1, and fix L now, and then for every value of L, ML can go from minus L plus 1 up to L. And MS of course can take eigenvalue is plus or minus half. Okay, all these are in units of h bar. Maybe if you want, I should put times h bar here, but that's not so important. So you can see that we have all these numbers. Exercise for you is do this counting, count all these. So this 2, I will do only the counting of 2. Any state with fixed n, L and ML will have 2 possibilities, this being plus and minus half. Okay, so that is the 2, and you just need to do this sum over n, sum over L, sum over ML, and show that that is n squared. That's an exercise for you. And the stationary eigenfunctions, again there is a length scale in this problem. If you just give me me and e square, which is the classical in classical physics, that's all we have. Once you go to quantum mechanics, you can construct a thing which has the dimensions of length, and we call that a, and this is something you know, it's called the Bohr radius. And then you can also write what is the wave function in position place of x. So ms can take plus or minus half, all the others I'm keeping. So you get some radial wave function, which is a function of only n and L, e power minus r by ma. Remember, r is just square root of x squared plus y squared plus z squared. And so r goes from 0 to infinity, so this is falling off exponentially, times some funny functions called spherical harmonics, and times the vector in spin space. So usually this is not written, but this is what you would have seen in your quantum chemistry course. But again, so this is some polynomial in r by a, and so on and so forth. Okay, so but again, here the idea here is to illustrate that we have this thing, and now if you give, I have the Hamiltonian, I can actually carry out the time evolution of these systems and ask what happens, so on and so forth. Okay, but again, that's not something we're going to do. So now let's just complete with a recap. We had 3 questions for quantum physics. First one is, how do you specify the state of a system? Then can we predict its time state at a later time? And the last one is about making physical quantities and how to make measurements. And we have given answers to 1 and 2. So the state of the system is a vector in a Hilbert space up to overall normalization. And psi hat, now I remember I was using hat to indicate that it's normalized and belongs to the Hilbert space H. And by the way, this hat is not a standard convention, it's just made for this lecture. And the time evolution is given by the Schrodinger equation, which is I h bar d by dt of psi of t is h of t psi of t. And if you integrate this, you get psi of t equal to u of t 0 psi of 0. So in the postulate, original postulate, we started with this as the definition, this line as the definition, and derived this. But actually, you can change the postulate to start with Schrodinger equation, and it implies this thing. And u of t0 is a unitary operator and hence non-preserving. So the next lecture is where we will answer question 3.